thank you for the organizer. I'm very happy to be here, and obviously any comments are welcome. And this is a joint work with Yakov Babichenko from the Technion and Fedor Sandomirskiy, who just completed 3 years here at the Technion, and unfortunately for us, he's moving to Caltech and he's about to start a postdoc there very soon. And this is about, the talk is about persuasion with mediators. So yeah, it's part of the literature on, the topic is related to strategic information transmission that has been studied for decades. We have the early work of Uman and Maschler about strategic information disclosure in zero-sum games with incomplete information on one side, and also the chip talk models, and finally, more recently, many papers about Bayesian persuasion. So what we are going to do is to consider situations where mediators are present in the communication procedure. So in many cases, the informed side and the side that takes an actions are communicate via mediators. And one example is politicians who want to share information with the public. He should do it via the media, but the media has its own incentives, and he should take that incentives into account when he shares information, because he knows that this information is not going to be communicated directly with the public. So this is one example, and one can think of a more complicated hierarchy of information transmission. And basically, what we are interested is the Bayesian persuasion model with the presence of mediators. And the question is mainly that we are going to study mainly will be related to the best sender subgame perfect equilibrium. This is in line with many of the Bayesian persuasion literature. So perhaps before getting into the formal models and everything, one picture that should be in mind of the speakers is the following. So we have a sender that is communicate privately with the first mediator, who can then communicate privately with another mediator, and so forth, until the information is transmitted to a receiver, who then takes an action, and everybody gets a utility. So this is the picture. And just clearly, the literature on Bayesian persuasion is very rich now, and there are many models. So there are some related work that I'm going to mention. Persuasion and mediators has been studied. One example is Kusenko, who studied one mediator and a persuasion setting with one mediator, but in contrast to what we do, he considered a simultaneous policy choice, where what makes his model more like a chip talk model. And Kwang et al. Also considered also integrated mediators to the persuasion setting. They were concerned with reputation issues. And we have the early works by Ivanov and Ambrus and Kian, who integrated mediators into the standard chip talk models. So this is more or less the conceptually related. I think technically the paper by Lee and Norman is very related. In their setting, the setting is similar to us. There is a sequential information revelation, but in contrast with our model, in their sequence of information revelation, the entire sequence can observe the state. So in their setting, information is being accumulated because every sender add more information to what is known so far. One can think of it like this. Whereas in our setting, information is being garbled. So the mediator gets the information only from his predecessor. He knows nothing more than that. So clearly the only thing he can do is just garble the information further. Finally, I want to mention the connection of this paper with the literature on persuasion with inattentive receiver. And the connection is slightly indirect because essentially we end up solving problem where persuasion problem with some constraint, and this is related to what they do. They end up more or less solving the similar problem, and this is the connection. Okay, so let me start unless there are any questions. Questions so far? By the way, now that I'm with full screen, I didn't think about it, but I cannot see the time. So Yakov, if you can tell me, or like sure. 2 minutes, or somehow I don't see it. Okay, so let's just
Itai, just a quick comment before you get into the model. Because you use the media as a sort of a setting for which your model would apply, it feels to me that media sometimes do their own research and add information to the reports, right?
Yeah, fair enough. Yeah, in some cases this is true. But, in our case, we study situations where the reporting side is the only informed party. So we consider a situation where the media cannot gather the information for other sources. I guess this gives rise maybe to other models, which is valid, but what we have in mind is a situation where the information is received sequentially, and every mediator gets information from his direct predecessor only.
And so, sorry, to follow up on that, you will have many mediators, but you will only have one sender, right?
Yeah, yeah.
Because that would have been a natural way in which you could augment that by adding senders who are basically always revealing their information truthfully to the mediator, and then the mediator would have basically an additional source of information. So that would be one way in which you could, complement the modeling.
Yes, so the paper by Lee and Norman considers a sequence of senders. So the entire sequence is of agents who are fully informed. And so the information is being accumulated, everybody. But we, in contrast, consider a sequence of mediators where the mediator cannot generate his own information. He just can gather the information he receives from the predecessor. Okay, so just for the model, so we have a finite state space, and the state is drawn according to a common prior. We have a sender and receiver, as always, and in contrast with the standard persuasion models, we have also n mediators. So the receiver takes an action, and the utility of all agents in the game is a function from the action of the receiver, the state, and the state. to the real numbers. Only the sender observes the realized state. The sender reveals some information about the realized state to the first mediator, who in his turn signals some information to the second, and so on. And then the last mediator communicates with the receivers, who takes an action. Now, we can think more formally about this game as having two stages. The first stage, there is a public commitment stage where all the mediators and the senders sequentially commit to how information is going to be revealed. And after this commitment stage, the state is realized and all the information is revealed according to the information that is committed to. So formally, the sender's strategies, in this case, or policy, is a function from the states of the world to some that generate information in some abstract signal state. And every mediator, the information of every mediator is yet again a function from some signal state, signal space to lotteries over, or to probability distribution over another signal state. So for simplicity, one can think of the signal space as the set of distribution over omega, and the information as being direct, namely if I receive a signal which equals some posterior mu, my posterior is exactly my signal. So this is the standard, and this is the setting. Am I understood?
Mm-hmm. Itai, may I ask one question? So this has a little bit of flavor of dynamic programming as you go forward, right?
Yeah.
And so you could ask yourself whether you could fold all of these mediators plus the sender in exactly one sender who has a specific utility function, so that in the end, his information policy is going to be equivalent to the sequence of.
Yeah, that's a very good question. I believe that some of the result will be in flavor of your question. So right. I want to postpone this discussion to a later stage in the talk, but this is an excellent question. And clearly, as we will see soon, the flavor of what you said is going to happen. So what we have, again, we have the indirect utilities for all the participants in the game, but for the receiver, which is the expected utility evaluated at the best reply action of the receiver. I think I don't need to introduce this. I think maybe one thing that I want to say is that we assume that these indirect utilities are not just upper semi-continuous, but continuous. And we can relax this assumption, but instead of talking about perfect Bayesian subgain perfect equilibrium, we'll have to talk about approximate equilibrium, because in general, this equilibrium may not exist if we don't assume continuity. So we assume that these indirect utilities are continuous, and indeed, in some cases, it happens if the action set is rich enough and it changes continuously in the prior, then it will indeed hold. But this is a technical assumption that we need. So, okay, now a definition. I will start with the case of a single mediator, which, as we will hopefully see soon, is different than the case of multiple mediator, or more than one mediator. So in the case of a single mediator, we have sender, receiver, and mediator. And let me offer a definition. So a set of omega posterior are said to be affine dominating with respect to a function f if for every set of weights over this posterior, one have that the convex combination of F evaluating at those posterior is always higher than the than F evaluated at the convex combination of the posterior. Or graphically, it's very easy to think about it. This happens whenever if we look at the graph of F, it is the case that if you look at the convex hole or the affine hole through the posteriors Q1 to QM, then this affine hole lies above the graph of the function F. It does not touches the graph of F. So in two-dimensional, I think in two-dimensional space, I will just demonstrate this. And so we can now define we now define a notion of concavification. So we let O be the set of all posteriors that are affine dominating with respect to the indirect utility of the mediator. So we restrict attention to the subsets of posteriors which are affine dominating. And we define this constrained concavification as the maximum value that can be guaranteed by the sender, restricted to policies that are lean on subsets of posterior that are affine dominating with respect to the mediator. So instead of taking the full concavification, now I constrain myself to only take concavification of sets of points which are affine dominating with respect to the mediator. And the first result is that the sender's optimal pave is equal to this constrained concavification. And the best way to illustrate this theorem, I think, is via a very simple example. So maybe I will present the example and then take question. So consider this indirect utility of the sender. And without the mediator, we have the standard concavification. Note that to achieve this concavification, one needs to generate posterior distribution that lies on 0.2 and 0.8. Now, assume that we have the following mediator.
Sorry, Itai,
So,
can I just go back the optimization that you defined before?
Yeah.
What are the objects that you're maximizing with respect to? With respect to mu and q, or?
So what I'm doing here, I'm considering all the mu tuples of posteriors which are affine dominating with respect to the mediator. Okay? Now I'm looking only on these subsets, and I'm looking at a convex combination of this indirected utility of the mediator evaluated at this posterior, subject to the constraint, the standard Bayesian persuasion constraint, that the average posterior is the prior. This is the last constraint that is, and the sender is simply maximize his utility upon all these such object here. It should be VM, the indirect utility of the mediator. Essentially not necessarily, but this is defined as the constraint concavification with respect to the indirect utility V. Is it clear?
Yeah, thank you.
Does this imply that the mediator does nothing? Will the mediator then be transparent?
No, not necessarily.
Not necessarily. Okay.
Not necessarily. It related to what Derek just asked, but which I will soon answer, hopefully. But let me just come back to the example. So we have this is what happened without mediator. Now, consider this guy as the mediator. In this case, a pair of points are often dominating with respect to this utility if and only if the line that goes through them is above the graph of the function. So the pair point to point end is not often dominating pair. So the sender can no longer achieve the standard concavification. He will have to choose pairs which are often dominating, which is now makes the concavification or the optimal value as the function of the posterior look different and compatible with what the lower picture. So this is how the new constrained concavification looks like with the presence of a mediator. Okay, so now I would like to give you a flavor of the proof of the theorem, unless do I have a question? Any question?
Yes, maybe you will talk about it later on, but I wonder how easy it is to compute this constraint concavification.
I will directly transform your question to Yakov, but so Yakov will answer this at the end. I guess it's difficult. I guess he would say it's not easy, but since he knows about complexity issues much better than I will not risk my reputation in trying to answer this. But let me just quickly go through the proof idea. So as Derek suggested, essentially, and this is this is true also for the paper of Lee and Norman that I mentioned. Essentially, we can consider equilibrium where no information is garbled through the process. So we can restrict attention to equilibrium when all the garbling is done by the sender. And then what the other mediator does, and this is true for more than one mediator as well, but what the other mediator does is essentially fully reveal all the entire information that he received from the previous mediator. So I guess it's easy to believe that one can restrict to this type of equilibrium. Now, the second part of the proof shows that an equilibrium, if we're looking at the support of the equilibrium is fully revealing mediator if and only if it lies on the support of points which are often dominating with respect to the mediator. And the fact that only omega signals are required to implement such a policy shouldn't be taken for granted. This is the core of the proof first. Second, as we shall see soon, this is not true when we have more than one mediator. Well, if we have more than, so it's not that we can easily apply the standard extreme point consideration to restrict attention to posteriors which contains only omega point. This is not the case. But still, with only one mediator, this is true. So yeah. So now, Yakov, did you say anything?
Yeah, 5 minutes.
5 minutes. Okay, perfect. Okay, so now this logic can be applied to the case where there are two mediators, right? We can look at all the points, the set of points which are affine dominating with respect to both mediator, and hopefully apply the same logic and restrict and maximize the utility of the sender with respect to those points which are affine dominating with respect to both mediators. This is true that the sender can achieve this value, but the characterization no longer holds with two mediators. So the sender can do much better. And this shows the non-monotonicity or information for the sender with the presence of mediator. So let's look at the following example, and I think I won't have the time for much more than that. So in this example, this is the utility of the sender, and this is the utility of the first mediator. So clearly, it cannot, the prior is half, and it's again binary state space, and the sender can no longer achieve the concavification because with this single mediator, because this mediator, what he will do, in order to achieve the concavification, the sender should pass along the entire information he received, namely, he should reveal the state to the mediator. But in this case, the mediator will gather the information and achieve a better outcome. So the value, as follow from our theorem, in half is the line that joining 1, 0 to somehow some point in near 0.25. So in this case, we have less than the concavification. But now what happened if we had a third mediator, a second mediator, sorry, with a utility which is equals the one that is depicted below? I claim that in this case, the sender can regain his full utility. And why is that? So now think about what would happen if the first mediator will gather the information to 2.5 and say 1. In this case, the second mediator will provide a further gabbling or full gabbling of the information and simply won't reveal any information to the receiver, in which case his posterior will lie at 0.5 exactly, and he will gain something more than he would have gained when he would pass along the information of this first mediator. This outcome is very bad for the first mediator, and one can show that he's better off transforming the information as it is. And so we show that more mediators are not necessarily bad for the sender. It's non-monotonic his utility is a non-monotonic function within the number of mediators. It can increase and decrease, and it shows that finding the optimal value with the presence of more than one mediator is slightly more intricate problem. And indeed, we have a further example that in this case, the optimal value can be achieved in a situation when there are more than two signals. So basically, we have an example where the optimal value for the sender is achieved in a policy that lies on 3 different posteriors and cannot cannot be further reduced to binary support. So we do have a solution, a recursive solution for the case of more than one mediator. So I'm not sure I have time to, with Yakov, do I have time to go over it? No. So we do have a solution, a recursive solution. It is less illuminating than the case of a single mediator, but we can say something about this case as well. So thank you very much, and that's it.
Thank you. maybe let me answer the question that Xiaoshen asked about the how hard is to compute it. So I think the issue is whether you are interested in computing the exact value or an approximate. So for an approximate, you can just, at least in low dimensional state spaces, you can just discretize the space, and for each, namely, which essentially corresponds to the case where you restrict sender to send policies with a given posterior that lies on a given grid in a small enough grid, and then you can just apply exhaustive search and find an epsilon optimal solution. In high dimensions, it's definitely hard, but even the standard concavification is hard. Even the standard question. About the problem of computing an exact, then you get into details how exactly is your function is represented, but yeah, I'm not sure that there will be a positive answer for that.
I was more curious about how hard it is sort of on top of the difficulty that already goes into the standard concavification, in the sense that one could imagine, I'm not sure it applies to your setting, but one could imagine that somehow the sender's utility function, the mediators, can be put together in some way, and then one applies concavification or some other method to that aggregate function, which by some chance lead to the same results that you have. I was more curious about this part.
So in this sense, so essentially, yeah, I guess that informally it is harder than just computing standard concavification, but I don't know how exactly to capture.
So I want to conclude. There was a question in the chat whether the value depends on the order of mediator, and exactly the last example I ended with shows that the value for the sender is dependent in the order of the mediator. If we switch the mediator, the value would have been different. So that's it.
Where did you use the continuity? In which of the two observations?
In both, because the problem with the discontinuity is that the receiver has to choose in favor of which of the mediator he breaks ties. So you want him to break ties. This is the standard assumption in Bayesian persuasion. I break ties in favor of the sender. But now we have mediator, so it's not clear who in favor of who you break ties, right? If there is some disagreement between the mediator, so